All right, today is our last section of new material, section 211, and we're going to look a little bit more at the Cartesian coordinate system. And the first thing we're going to take a look at is x and y intercepts. And we talked about them in the last section. We're going to talk about them a little bit more today. So we're going to find the x and the y intercepts, and then we're going to use them to graph the equation of the line. So if you'll remember, to find the x intercepts, what do we have to do? Right, we have to let y equal to 0. So in our equation, we have 2x minus, and then I've got a 0 equals 4. And as we're looking at this then, of course, that 0 goes away. So now I just have 2x equals 4. And if I divide by 2, what is x?
2.
2. And then the x-intercept is always written as an ordered pair. X is 2, and y is 0. And then we would have our y-intercept. So the y-intercept then would be where x is equal to 0. So I have 2 times 0 minus y equals 4. So 2 times 0, that's now 0. And now I have negative y equals 4. How do I solve for y? Yeah, move the negative. We either divide by -1, multiply by -1. Think about it a couple different ways. And we end up getting that y is -4. So what is my y-intercept?
0, -4.
Right, 0, -4. So these are the x and the y-intercepts. And then we're going to plot them on the line. So when we started the last lesson, you could choose any values that you wanted for x and for y and plot them. And that's certainly one way to graph a line. There's nothing wrong with that. On this one, since I'm asked for x and y intercepts already, I might as well use those to plot. So I can plot those points. So x equals 2, y is 0 would be right here. And then x is 0, y is -4 would be right here. And then we're going to connect them with a line. And it looks something like that. Okay, all good? Okay. So we don't have to have just general points. We can use very specific points if we have them as well. All right, so when we were looking in the last section, we were mostly looking at, in fact, maybe completely and totally looking at lines, just like the last one. What we're going to be looking at in this section is going to be a bit broader description of graphs. So we're going to look at example number 2. It looks like I accidentally erased my screen from this, probably somewhere along the way. So let me draw in the picture that's on your screen. Let's see, I have -2, 2. And then it goes through 4 and through 0. Okay, so this is the graph that you have to start with. Is that right? No? Okay, draw it in then. Okay, that's probably because I couldn't get the graph to show up the way I wanted to when I was looking at it inside of Word too. That's right. It looked like it was so good. It looks so good on here. It looked like it was printed, not written by me. Isn't that nice? Okay, so draw that in. So the graph has a kind of a corner right here at -2, 2, and then it crosses at -4, and it crosses at the origin. This is a specific type of graph. You might have seen it before. If you haven't, it's no big deal, but it's an absolute value graph, actually. The question remains, with what it's asking, though, is just to simply find x and y intercepts. So this is a graphical one, so we're just looking from a graphical standpoint. So we'll start with x-intercepts. What are the x-intercepts for this graph?
-4, 0, and 0, 0.
Right. -4, 0. That's right over here. And then 0, 0 right there. So I have 2 x-intercepts. That doesn't happen when we have lines. You just always have one or none at all. But when we have other curves, we can have more than one. How about y-intercept? What's my y-intercept?
0, 2.
Yeah, no, not 0, 2.
0, 0.
0, 0, yeah. So it's still where it crosses the y-axis, and the y-axis is still the origin right here. That's where it's crossing my line right here. This vertical line is still at the origin, 0, 0. So my x-intercept and my y-intercept happen to be the same thing. That happens occasionally, but only if it's 0, 0 would that happen. So this is taking a look at a graph and identifying the x and the y-intercepts. Now we're going to take a look at some equations and do the same thing. Now the process is just like it was with the lines. It's just harder because it's not a line. That's really what it is. It's just harder. So we're going to still find x-intercepts by letting y equal 0 and y-intercepts by letting x equal 0. So it lists x first, so I'll find my x-intercepts first. So my x-intercept, which is when y is equal to 0, is where I'll start. So this is 0 squared plus x minus 16 equals 0. And 0 squared, of course, goes away. So what would I need to do to solve x minus 16 equals 0?
Add 16.
Yep, add 16. Whoops. So x is equal to 16, giving me my x-intercept, which is
16, 0.
16, 0. Okay, y-intercept. So the y-intercept now is where x is equal to 0. So I have y squared plus 0 minus 16 equals 0. That 0 is going to go away. So now I just have y squared minus 16 equals 0. What would I do next?
Add 16.
Add my 16, just like on the other problem, or other part of this problem. So it now tells me that y squared is equal to 16, but I don't care what y squared is, at least not really. I want to know what y is. So what do I do to solve for y?
Square root.
Yeah, I take a square root. So on the left, I get just y, but what happens when I put a square root into a problem? I don't think we've talked about this before. Do you know? Some of you have tried to do this when the square root started. Yeah. When a square root is already in the problem, right, it starts out having a square root, which we've seen that happen. It's called the principal square root, and it means it's just the positive part. But when we insert a square root into a situation where there wasn't one to start with, we don't care that it's just the positive part. It's either one. So if we put a square root onto a problem, we have to put plus or minus. And then what is the square root of 16?
4.
It's 4. So there's actually two y values that came out of this, right? 4 and negative 4. And if you think back to the equation itself, that would actually make sense, because if I had, we'll just use the first one where I put in the 0 from the top of this line of it. If I put in 4 squared is 16, 16 minus 16 is 0. But if I put in negative 4, what's negative 4 squared? 16, right? Because a negative times a negative is a positive, and then 16 minus 16 is again 0. So on this one, I have two y-intercepts. I have the y-intercept 0, 4, and I have the y-intercept 0, negative 4. I don't have negative 4, 4, or 4, negative 4. I don't put the y's together, right? It's still x and then y. Yes?
Do we need to list it as two separate points, or can we do plus minus 4?
You can put in plus minus 4 if you'd like. I'm okay with that. If you want to write it this way, that would be okay. Sure. Okay, so either of those options, I have my x-intercept found and I have my y-intercept found. Okay, ready to take a look at the next one? Okay, so this is called a rational function. I say ratio, fractions. We've looked at ratios or rational functions and talking about adding them and subtracting them and things like that, multiplying. This time we're actually looking at the intercepts for it. The process is still the same on the front end. So the x-intercept is where y is equal to 0. So y is equal to 0 means the left-hand side, that's y, is equal to 0. Okay, is that okay for starters? Just put 0 in for y. This is something I need to solve, and I can write it as 0 over 1 if you prefer. And one of the ways in which to think about this, and there's more than one, but one of the ways in which to think about this is I can cross multiply. Does that make sense? So I can actually multiply, let me shift this up because it looks all funny. I can multiply across my diagonals. I'll talk about a couple ways that I can think about this in a moment, but this would give me 0 times the 5 plus x squared, which is just 0. And then it would give me, actually, let me write it in for this time. You don't have to write that in, but if you wish to see it, you can. And then I have the 1 times 1 minus x squared. So this is one way to think about it. That 0 is everything out on the left, because when you multiply by 0, you get 0. And over here, I have 1 minus x squared. So let me pause there for just a second. We're going to finish solving this, but let me tell you a couple other ways you can think about this. If you don't want to think about this as cross-multiplying, you can think about it as multiplying by the denominator to both sides. If I multiply the denominator on both sides of this, This still goes away because I'm multiplying by 0. A third way to think about this is the fact that the only way a fraction can be 0 is if the numerator is 0. It doesn't matter what the denominator is. If the numerator is not 0, the fraction's not 0. So you could just say, oh, if I want the whole fraction to equal 0, I need the numerator to equal 0 and get to the same spot. Any of those three ways will end you up at 0 equals 1 minus x squared. What would you do next? How about we move the x squared? It's negative. If I move it, it'll become positive. That's kind of friendly. Is that okay? What would I do here? Square root it. And Gregory, when I take a square root, what do I have to do? Do you remember? Just forgot. Somebody help him out. What do I have to do when I put a square root on a problem? A plus or minus. Yeah, so anytime I put the square root or I insert the square root into the problem, I put plus or minus. What is the square root of 1? 1. Just 1. It's not a trick question, no. All right, so I actually have two values for the x values here. Y is still 0. So I have the x-intercepts 1, 0 and negative 1, 0. Or like Simon asked, if you want to write plus or minus 1, comma 0, you could do that as well. These are my x-intercepts. All right, so now I have to do my y-intercepts. So my y-intercept is when x is equal to 0. So I have 1 minus 0 squared over 5 plus 0 squared. So these zeros are both gone. What is y? 1/5. So what is my y-intercept?
0, 1/5.
0, 1/5. Okay, all good? Okay. Most of the things that we're ending with talk about how to graph equations. We've talked about graphing equations in the previous sections, but they're specifically equations of lines. And in order to graph a line, all you need are 2 points. And you got it. Like there's nothing else to do. 2 points, connect them, with a ruler, and you're good to go. That doesn't happen if you don't have a line. And so when we're graphing non-lines, right, anything else that's not linear, we need at least 5 points. And you might even want more if you're not quite sure if you've got the right idea. You guys have access to graphing calculators, and that's fine as well. I don't have a problem with you referring to your graphing calculator. But your graph has to show at least 5 plotted points on there to establish that you understand how the process is working. Okay, at least 5 plotted points. Often, not always, but often the x values -2, -1, 0, 1, and 2 are good choices. Not always, but often. They're a good place to start if you don't know where else to start. So we're going to be graphing some non-linear equations. And the first one is actually an absolute value. I mentioned that earlier on, that we had the picture on number 2 of a graph of an absolute value function. So this equation says y equals 3, and then it has the absolute value of x. So as we plug numbers in, we're plugging our x values. We're going to pick those x values that I mentioned on the previous screen as being potentially good choices, and they will be on this one. And we're putting them in, -2, -1, 0, 1, and 2 in for x. And we're going to figure out what y is at each of those locations. So over here, I have my equation. It's too high for me to actually point to, but over here. And I'm going to change the value inside each time. I'm going to just start with the -2. What's the absolute value of -2? 2. And what's 2 times the 3 in front? 6. So in my table, this is the value 6. And we're just going to go down the line. -1. What's the absolute value of -1? 1, and then multiplied by the 3 is going to give me the 3, right? How about 0? What's the absolute value of 0? 0. And 0 times the 3 is still 0. 1. Absolute value 1 is 1. And then 1 times the 3 in front? 3. And then the absolute value of 2? 2 times the 3 in front? 6. So here are 5 points, and we're going to plot them. Okay, so we're going to plot negative 2, 6, negative 1, 3, 0, 0, 1, 3, and 2, 6. Does it look like a V? Yeah, it will, and we're going to connect it so that it does. Anytime you have an absolute value graph, it is going to look like a V. And what's actually happening, I'd kind of like to just show you because it's really not a mystery, but it sort of seems maybe non-intuitive, is that if I had drawn the graph of just y equals 3x, it would have looked like this. Hang on. Okay, the red line is y equals 3x. Don't draw it on your paper, but that's what y equals 3x would look like. And what absolute value does is it takes everything that's below the x-axis and it flips it up to above the x-axis. Right, so everything that looks like this is now flipped up here, and that's how I have my V shape. Okay, that's what's happening when I work with absolute values, is I get a V shape. So make yourself a note that all absolute values will look like V's. It's always going to be V-shaped for an absolute value graph. Okay, our next graph is going to feel a little bit similar when I plot my points, but it's not going to be a V. Why? Because it's not an absolute value. It's not an absolute value. It will not look like the shape of a V. If you've seen this graph before, I'm sure you have, do you remember maybe what it's called? There's a couple of things it can be called. We called it quadratic when we saw before, having an x squared. The shape of it looks like something called a parabola. Shake your head if you remember parabola, like you've heard that before. Most of you should have heard parabola before. It comes up. So we're doing the same thing. We're still plotting all the same points. All that's going to be the same. So we're going to create that chart, x and y, and I'm going to pick those same ordered pair points. You might be saying, well, okay, but how do I know when I can't pick them? And it's one of those things that's going to be like, you're going to know, because when you graph them, you're still not going to be sure how to quite connect them in what you're anticipating them to look like. Okay? But for the most part, these are going to be good points to pick. So I'm taking this equation now, and I'm putting numbers inside of something that I'm squaring. And after I square them, then I'm going to make them negative. Okay, that's what the negative on the outside is going to do. So in essence, all of my y values are going to be negative, right? No matter what I square, I get a positive, and then I'm going to multiply it by a negative. So all of my answers down here are going to be negative. Well, not 0, because it's going to be 0, but everything else is. Yeah, negative 0, which is still 0, yeah. All right, so if I take the number negative 2, what is negative 2 squared?
4.
4. And then I multiply it by the negative, making it a negative 4. What is negative 1 squared? 1. And then multiply by my 1, making it a negative 1. 0 squared? 0. And then the opposite of 0 is still 0. How about 1 squared?
Same thing.
Chase says it's 5. It's 1. Yeah, 1, and then multiplied by my negative makes it negative 1. And then how about 2 squared?
Same thing.
Same thing, I got a 4. Okay, so these are my points I'm going to plot. I have negative 2, negative 4. I have negative 1, negative 1. I'm sorry, yeah. I have 0, 0, 1, negative 1, and 2, 4. And it almost looks like a V, right? It almost does, but the ratio isn't the same. If you take a look over here, I'd like for you to notice what happens is that I go right 1 and up 1. 3, excuse me. Right 1 and up 3. Right 1 and up 3. Right 1 and up 3. And it works the whole time. It's consistent, right? Constant. The whole time I'm going up and saying that at the same speed. I'm not doing that over here. On this one, if I go right one, I'll go down one, but then if I go right one more, I go down 3. That's not a V because it's not a constant change that I'm having happen. So how does this get connected? Well, I mentioned before a parabola, and that's terrible looking. Go like that. Looks something like this. There we go. So it's got a U kind of a shape. So anytime you see x squared, you should be thinking you've got a, hang on, we'll do it like this, a U shape. It's a U shape. All right. So what shape is number 7 going to be? A U shape, right? How does number 7 differ from number 6?
Adds 5.
It adds 5. Now, when you're in college algebra, you're going to talk more about what adding the 5 at the end does, but it's going to change it some, but the shape shouldn't change. It's still going to be a U. So we're going to still have the same ordered pairs we had before, or at least the x values. I have -2, -1, 0, 1, and 2. They work just fine. And I'm going to do the same thing. I'm going to put a number in, I'm going to square it, and then I'm going to make multiplied by a negative value, and then I'm going to add 5 to it. Now, because we've already got this list over here, you can imagine taking each of these values, because that's the negative x squared part, and adding 5 to it. If you didn't already have this list, you'd have to do it from scratch. So I'll say it from scratch, but what I'm really doing, since I do already have this list, is adding 5 to all of these y's. So if we were doing it from scratch, what is -2 squared? 4. I'll actually write a few of these down at the beginning. -2 squared is 4. I have a negative on the 4. All right, so now it's -4. And if I take -4 and I add 5, I get 1. -1 squared is 1. With the negative in front makes it a -1. What is -1 plus 5? 4. 0 is lovely. 0 is always, a good thing to pick when you have that option. 0 squared is 0. The opposite of 0 is 0, and 0 plus 5 is 5. Now, if I put in the number 1 and I put in the number -1, the same thing happens as when I put in the if I put in the number -1, the same thing happens as what happens when I put in the number 1, right? Because signs don't change. So when I put in the 1 squared is 1. The negative in front of it makes it -1, and the 5 afterwards gives me another 4. And the same thing for the number 2, I get the number 1. So as I'm evaluating those and plugging those in, I get the same thing whether it was positive or negative. So I'm going to plot those -2, 1, -1, 4, 0, 5, 1, 4, and 1, 1. I'm sorry, 2, 1. And I connected in that same U shape that I had before-ish. Looks like that. Okay. Do you see that I've got 5 points plotted on my graph? Do you see that? Yeah, about 7 of you are just not going to plot points for me, and I'm going to take off all these points, and you're going to be like, what? I'm going to be like, I told you. You have to plot the points. Okay, you're going to plot the points on the graph. They're going to match your list of values. That's the work you're showing on these problems. It's not difficult work. It's not complicated work. Just do it. Okay, move past the problems. Just do it. Okay, this one's a little different. This one is a cubic one, right? I've got cubed. It's kind of messy because the values are kind of messy to pick. I'm still going to pick the same -2, -1, 0, 1, and 2. You might be asking, do I have to pick those values? And the answer is no. If you wanted to pick something different, you certainly could. On this one, it gets a little bit messy because if I pick a number that cancels with the denominator really nicely, it might end up being off the graph, like the grid that's already marked for me in the homework. So be aware of that. You want to make sure you're still on the grid of what you're being given. So I'm still going to pick the same values that we did before. But again, recognize that you don't have to, but they'll work. Okay, so we're going to start with -2. So I have the same thing I did before, where I'm leaving this sort of space in here, and then I'm cubing something. Okay, so if I put in -2, what is -2 cubed? Good. -2 cubed is -8. So 3/4 times -8. What is 3/4 times -8? Feel free to grab a calculator if you want. It is -24/4, which would be...
Is it like 7? -7?
Close. -6. Yeah, -6. So this one gives me -6. Do -1. So 3/4 times -1 cubed. So what's -1 cubed? -1. It's still negative though, right? Okay, so -1. And what's -1 times the 3/4? Yeah, -3/4. So this is 3/4 times -1. So it's -3/4. What happens when I put in 0?
0.
I get 0. Putting in 1 looks a lot like putting in -1. How will it be different? I'll write it. Yeah, it's positive. So when I put in the 3/4 and I multiply by 1 cubed, the 1 cubed is actually 1, right? I don't have even the negative involved. So this is 3/4 times 1, so I just have 3/4. So what do you suppose is going to happen when I put in 2? Yeah, it just changes the sign and it'll be 6. Okay, you don't have to show the work of plugging these in. That's not my goal. But I do want to see the list of values that you end up with, okay? So feel free to grab a calculator to put those in. That's fine. These are my 5 values I'll plot. Yep, Simon?
If we have the list, just the x and y side.
Yep.
And we have to show all the points. Do we have to then turn those into points, or is that good enough to show that it's the x and the y?
Like a list, but not in it. Show me what you mean.
So there's my list, and then there's the different points. Can we
You
just
don't even
keep
have to list the points. Yeah, you can just list the list like this. The list is fine. You don't have to write them as ordered pairs. Just write them on a list. Will be good. You are going to plot them on a graph, though, right? So we're going to get the graph. I've got a grid on my paper. Yours doesn't have one, but you can draw it in. It's okay. -2, -6 would be down here. -1, 3/4. Well, 3/4 is not on a grid mark, but it's somewhere between 0 and 1, right? Not 1 and 2. Well, 0 and 1. So it's about like right there-ish. I have 0, 0. I have 1 and then 3/4, and then I have 2 and 6. So these are my points. You may have seen this graph before. You may not have. If you haven't, it's no big deal. It always, again, will look like this. And it looks something like this when I connect the points. So imagine connecting the points in Chili's, but you're not connecting with line segments. It doesn't do this. Right? It doesn't do that, okay? Don't do that. It connects smoothly, and it connects looking something like this. That was pretty good, actually. Yeah. So this cubed graph always has this sort of, this kind of shape. I don't have a name for it. It's not really an S, but this shape happens when I have an x cubed graph. A snake. All right, we'll go with a snake. All right, we're really close to done, guys. All right, a few more things. Symmetry. This is our last thing in this section, symmetry. Symmetry talks about what a graph does in comparison to itself. So there are 3 types of symmetry that a graph can have. And we're going to go back and we're going to look at the ones we've done to decide if they have any of these. And then I'll show you a couple more because there's not examples of all of them. X-axis symmetry is a graph that's a reflection over the x-axis. Okay, so if you imagine having a graph that opens like this, like my hand's opening upward, the reflection would be over the x-axis would be that it opens downward. Right, that's a reflection over the x-axis. All right, so the y-axis, right, so the y-axis is the vertical one, is the reflection that happens that, for the most part, is our bodies, right? So if you think of a line going from the tip of your head down straight through, between your feet, you have symmetry, more or less, right, within your own body. So left hand, right hand, symmetry. They match, okay? And then origin symmetry is symmetry around the origin. And what it means is you can spin it 180 degrees, and it lands back on itself. Okay, so imagine a spinner on a board game. You're thinking about that. These are the three types of symmetry that show up. They'll show up again, more detail in college algebra. We're just going to touch on them here. What we're going to do, is on your last 4 examples, is we're going to go back at the ones we were doing before and talk about the symmetry. And then there's one of the symmetries that doesn't show up, and I want to give you an example of them and a few others just to show some images, okay? So going back to problems 5, 6, and 7, and 8. This one, except for the red part.
Just says a node graph can have bunch of these or bunch of
Oh, I don't know. I guess I didn't get that typed in here. I apologize. That's true. There should be a note. And the note should say, a graph can have, I'll write it in, so sorry. A graph can have one of these, all of these, I know I'm abbreviating, but these are your blanks, or none of these. It can't have 2 of these. That's not possible. Okay, it's either 1, all, or none. So what these problems look like at the very end of your homework as you're looking is they look like multiple choice boxes, and you have to mark which ones they exist. Okay, so you could end up marking everything. You could end up marking just 2 things, or you can end up, one thing, or you can end up marking that none of them happen. Those are your choices. If you've marked 2 of them, you've done something wrong. Can't be just 2. All right, thank you so much for that. Looking at number 5, ignoring the red marks. I don't know if I can get them off or not at this point. Oh, I think I can. What symmetry do you see?
Y-axis.
It is y-axis. The y-axis itself right here splits the graph into 2 components that are identical, like mirror images on the right-hand side, the left-hand side. This is y-axis symmetry.
So those are, if we write down that, find your notes.
Yep, on your number 5. Yeah, your number 5 in your notes should say that this has y-axis symmetry. How about on number 6? Y-axis symmetry. It's the most common one. This one is y-axis symmetry. How about number 7? Why? Are you bored yet? Yeah, this is y-axis symmetry. I told you, it's the most common one. So this is, again, y-axis symmetry. The next one is not. This is not y-axis symmetry. It's origin. Can you imagine spinning this around 180 degrees? Right, a flip around, and it would land right back down on itself, right? This is origin symmetry. So all of my examples had only one type of symmetry. So what do things look like when they have none or all? So let me just draw a couple of examples. If something has no symmetry, right, none, most of your lines that we did would look like this. But they could even be graphs like what we just saw, like this absolute value graph. They're just not along the y-axis. They're shifted, right? That's no symmetry. There's symmetry within itself, but not within the y-axis. One that has all the symmetries. This is a really good example one. I didn't draw it well, but imagine that it does. Looks kind of like a football or an egg shape. It's called an ellipse, right? Can you fold it along the y-axis and it match? Yes. Yep. Can you fold it along the x-axis and it match? Yes. Can you spin it at 180 degrees and it match? Yes. This has all the symmetries. And then let me give you one that's an x-axis symmetry. This has x-axis symmetry. We don't see these come up very much because they fail to be what are called functions, which is a big component of algebra. But it's x-axis symmetry, right? It's a mirror image on top and on bottom of the x-axis. All right, that'll be it for today.